So before I just gave you one little argument here, example one of how you can use an invariant property to prove that two groups are not isomorphic. And of course what I used is I used the cyclic invariant, which we've used before. Now, of course, you can't prove every theorem in the world just by using the cyclic property over and over and over again. You can have two groups that are not isomorphic to each other, but they're still cyclic. So it's not going to help you. So you need other invariants in your toolbox. Luckily, this is not a joke, there are actually infinitely many invariants in group theory. So there's lots and lots and lots of tools in our toolbox. And what I thought I'd do is leave you with a short list of invariants, and then we'll talk about how you prove something's an invariant again, and then let you just play with this a bit. So here's a short list of some invariants here. For one, being abelian is an invariant. And it's a good philosophy to realize that anytime you have an invariant, so is its opposite. So if P is an invariant, so is not having P. That's also an invariant. So since being abelian is an invariant, well, so is being non-abelian. Right? So you can always get a new invariant from an old one by just negating it, saying you don't have it. Okay? So being non-abelian is an invariant. There's lots more. Having an element of order 2 is an invariant. Right? So 2 is not special. You can also say having an element of order m is an invariant. Okay, so if your group has an element of order 2, but your other group does not have any elements of order 2, well then they can't be isomorphic. If your group G has an element of order 14, but L does not have any elements of order 14, and you can prove that, well then G and L cannot be isomorphic. Okay. Instead of just saying that you have at least one, you can also say that you have k of them, right? So having 12 elements of order 3 would be an invariant. Having 29 elements of order 43 would be an invariant. You can even let m be infinity. Having 2 elements of order infinity is an invariant. You can even let k be 0, which means you have no elements of order m. That's an invariant. So those are all invariant properties. Having a non-trivial solution to x cubed is the identity. Of course, the identity E solves this, but having another solution, that would be an invariant. Having a subgroup of a specified index, that's an invariant. So having a subgroup of index 4, that would be an invariant. Having a subgroup of a certain isomorphism type is an invariant. So fix a group H. Having a subgroup that's isomorphic to H, that would be an invariant. Likewise, you can append normality as an extra adjective. Having a normal subgroup isomorphic to H is an invariant. So there are all kinds of invariants up here, and there's literally infinitely many more of them. Okay, so what I want to do is take 2 of these properties and argue that they are invariants. The rest of them you can take as good exercises. So the exercise is take an invariant like this one, having a subgroup of index m, for instance, and then prove that it's an invariant. Okay, so I think the best, beyond being cyclic, beyond the cyclicness in invariant property, the best invariant property to understand the strategy for how you prove it is being abelian. So let's do that together. Proposition 2 says that being abelian is an invariant of groups. Okay, if G is an abelian group and L happens to be isomorphic to G, then L must also be abelian. There's no escaping it. Let me walk you through the proof line by line. We'll prove another one later on down here in Prop 3, but I'll let you read that proof. I won't go through it. It's straightforward. But let's do Proposition 2's proof together. So you're supposed to prove that L is abelian. That's your job. Prove that L is abelian. And what do you know? What you know is that G is abelian. You know that much. And you know that G is isomorphic to L. And since you know they're isomorphic, you might need to use that isomorphism to prove the theorem. So since G and L are isomorphic, there exists an isomorphism. So get your hands on one. Suppose that alpha from G to L is an isomorphism. Okay? Your job is to prove that L is abelian. My job is to prove that if I take any 2 things from L, A and B, my job is to prove that A times B is always going to be the same thing as B times A. Okay, so take 2 elements A and B from L. I'm going to somehow argue that AB is BA. Okay, here we go. Well, A comes from L and G is onto, alpha is onto. So somebody from G has to hit A, so call it C, right? So alpha is onto, so there must be an element C back in G that hits A. Likewise, there must be an element that hits B, so there must be an element D back in G that hits B once you hit it with alpha, right? So that's just alpha being surjective. So you take A and B, alpha is onto, so there must exist a C and D with alpha C being A and alpha D being B. That's just the definition of being onto. That allows me to compute A times B. Well, A times B is alpha C times alpha D. There we go, A times B. But alpha is a homomorphism, so that's alpha of C times D. But C times D is happening within G, and G is abelian, so C times D is D times C. So replace that interior CD by this interior DC. But alpha is a homomorphism again, so that's alpha D, alpha C. But that's B times A, so I've proven that L is abelian. So notice that I had to use the fact that alpha was onto and that alpha was a homomorphism, all necessary ingredients of being an isomorphism. Okay, so that proves that L is abelian, and therefore being abelian is an invariant. In proposition 3, I prove that having k elements of order 2 is an invariant. And you can imagine how you would take this proof and replace the 2 by any m. So having k elements of order m would also be an invariant. And so I just do the same thing. Suppose that G has k elements of order 2, and suppose you write them down. Here are my k different elements of order 2. And then take an isomorphism. You're assuming that G is isomorphic to L, so grab an isomorphism. My job is to prove that L also has k distinct elements of order 2. And the proof is easy. You know that A1 had order 2 back in G. Your job is to produce elements of order 2 in L, so just push them forward under alpha. So take A1, apply alpha, call it B1. Take A2, apply alpha, call it B2. And then you argue that these guys are all different in L, so this is actually a list of k different elements. And then you argue that all these BIs are order 2, and they are, and you're done. So it's an invariant. So I'll leave it to you to prove that the rest of these guys are invariants. It's kind of fun. It's a good challenging exercise to make sure you know all your definitions. And then finally, I'm going to leave you with a good batch of practice problems that use isomorphisms and invariants. There's 9 of them here. Some of them are good and challenging. Some of them are straightforward. You should try to do all that you can to see if you can understand this material, okay? If we want to get together as a class and start having Zoom meetings and going over these, I am happy to do that at 10 o'clock Monday, Wednesday, Friday, any day up to and including your final exam day. And then if you want to meet otherwise, we can do that too. But I think it would be good for us to get together and talk about some of these and talk about some other problems going forward into your final. Okay, that's it. I am done with material. There are some things I'd like to do, but given the situation, I'm not going to do them. We're going to stop right here. This gives you 10 days to catch up with this material to finish the semester. Anything I wish we could do but we didn't, we'll do it in the fall. So I'll see you then, and let me know if you have any questions.